for the direct comparison test, you want to look at two sequences, AN and BN. So when a question is given on the direct comparison test, what you most likely be given is just AN, not both AN and BN. In most cases, you will have to define BN on your own, but you can define it based on AN and try to be smart about it. But for this comparison to work, you see, the relationship between our AN and the BN we define here has to be such that, firstly, 0 has to be less than AN. In other words, AN has to be greater than 0. Apart from that, the same AN has to be less than BN. So BN has to be greater than AN. So AN has to be greater than 0. BN has to be greater than AN. So this is the condition that we need. If we can define this, if we can come up with a BN that satisfies this condition, then it implies that for any value of n that you can pick, if the sum to infinity from n is equals to 1 of Bn, if this sum converges, then the sum from n is equals to 1 to infinity of An will also converge. So provided these satisfy this, then if Bn converges, even An converges. In the same way, if Bn does not converge, let's say Bn diverges, then even An will diverge. So if the sum up to infinity of Bn diverges, so will the sum to infinity from n is equals to 1 of An. Now, what is happening here? You see, we want to define Bn such that it is easy to evaluate. If we can define Bn to be something we can easily evaluate, then we can easily use that description or its state, whether it converges or diverges, to make conclusions about our An. Look at an example. Look at an example. Again, I'll use basic examples first, then we'll try to see if we can pick something complex. Suppose you have the sum to infinity, n is equals to 1, of 1 over 2 plus 3 to the power n. If you look at this one here, it might be difficult for you to actually see whether this converges or diverges. But if you could define something similar to this by all means, but maybe just different a little bit, that you might be able to easily conclude whether it diverges or converges, the world would be a better place. Now, what do I mean? You see, you can easily define, let's set this first of all to be our An. So our An is 1 over, then you have 2 plus 3 to the power n. Now, based on this An, clearly from An first, you can tell that regardless of what n is here, you can tell that this expression will never give you a negative. Can you see that? Can you see that that will never be negative, regardless of what n is?
Yes.
Yeah. So this clearly is greater than 0. So the first part of this has been satisfied. An is greater than 0. Now we want to define a second series, Bn, but we want this Bn to just be a little bit more than An. And we want it to be as close to this format as possible. And it has to be something whose convergence or divergence can easily be discussed. How do we do that? Well, I noticed one thing. When you look at this expression, it would be easy for you to actually conclude whether it converges or diverges if only that 2 in the denominator was not there. Look at this. This is similar to something we have seen before, but what makes it different is that 2 being present. If only the 2 was not there, if only we had this, notice that this would look similar to a type of sequence that we have seen before. What sequence is it? What sequence looks similar to this? How about if I did it like this? If I just remove the 3 there and put, yeah. Notice that when I put a 2 here, it becomes the one where we ended up with 1 over 2 raised to the power n. Do you remember this one? I think we did this one a little bit earlier. This one, where we had 1 over 2 to the power n. The only difference is now this is a 3 to the power n. So by observing this, I see that if only the 2 was not present, then the 1 over 3 to the power n would be close, or it not close, it would be seen as a geometric sequence. So what I do is, I then define Bn to be equals to 1 over 3 to the power n, without that 2 first. But for this to be a correct approach, it must be such that my Bn has to be greater than An, so that it satisfies that condition that we defined earlier. So which one is bigger? 1 over 2 plus 3 to the power n, or 1 over 3 to the power n for any value of n? Which one will be bigger? So you have to see that this is the bigger one. Why? Because the denominator is a little bit too much. The denominator is a little bit too much. So when you divide a big number into 1, you get something small. But when you divide something which is a little bit small into 1, you get something a little bit big. What do I mean? If this was 1 over 1,000, you'd get 0.001. But if this, let's say, was smaller than this, let's set it to be, let's say, over 100, clearly this one would give you 0.01. So if you compared which one is bigger between 1 over 1,000 over 1 over 100, clearly 1 over 100 is bigger than 1 over 1,000. So this 2 plus 3 to the power n will be bigger than 3, as in 1, it will be bigger than 3 to the power n. So because of that, when I divide both terms into 1, this side I'll get something smaller. This side I'll get something a little bit bigger. Does that make sense?
Yes.
Great. I thought it didn't make sense. When I said it made sense to me first, then I thought of myself as a student, I was like, it doesn't make sense to me. But since it makes sense to you guys, then it's okay. Okay, so based on that logic, we can conclude that this Bn we have selected actually plays a good role here. 0 is less than our An, which is 2 plus 3 to the power n. And this An is also less than our Bn, which is 3 to the power n. Because these are satisfied, this allows us to use the direct comparison. What is this comparison? Whatever the state of our Bn will automatically become the state of our An. So all we have to do here is determine whether our Bn converges or diverges. If it converges, even An converges. If it diverges, even An diverges. So let's look at our Bn. Bn is 1 over 3 to the power n. Does this diverge or converge? What do you guys think? So if you look at this one, let me not write it like this. That is what Bn is, yes. But as a geometric sequence, we have n is equals to 1 to infinity of 1 over 3 to the power n. Just like in the earlier example we did under geometric series, we see that this is the same as 1 over. Firstly, let me say the sum, 1 to infinity, and then this will be 1, the value of a, and then the value of r becomes 1 over 3 to the power n. So our r here becomes 1 over 3. So you see that our r lies within this range. And since it lies within this range, according to the geometric series, it means that this converges. So we then conclude that since Bn converges, even An will. An converges. So that would be our conclusion. Is that okay?
Yes, it is. So the question, how can we tell when to use the direct comparison test and when to use the p-series and when to use the geometric series and whatnot?
I think you should have seen the pattern so far. Let me show you. Geometric, we must somehow end up with a sequence. This can start from 0. Usually we start from 0 for this one. But the key thing is it should be possible for you to write I mean, raised to some power n, where n is a positive power. For P series, it borders on you being able to have 1 over, and then you have n as the base to the power some constant p. P is a positive real number. And then for this direct comparison, it works with expressions whose convergence and divergence cannot be evaluated easily. So we decide to compare them with expressions which we can evaluate easily. Like if, let's say, I had the sum, and then instead of, let's say, what we had earlier on in the previous example, we had, was it equals to 1 up to infinity? I don't know really what we had there, but I think we had 1 over, and this was 3 plus, and this was, that was 3 to the power n. Now, what if we had, instead of that, what if we had n to the power 3? Which one do you think would have used here? Of course, when you look at it the way it is, we cannot use geometric. We cannot use P series here, but we can compare this to something that looks either geometric or P series. So we'll compare it with what? Something that looks like what? Geometric or P?
P.
Exactly. Why did you say P? Because here you end up with n to the power a constant. In the previous case, you ended up with plus, it was a constant raised to n. You see this? Geometric will always have a constant raised to n. P will have n raised to a constant. Do you get that, Mapalo?
Yes, I do.
Yeah. So for this one, the comparison would be with Bn, which would be equal to 1 over n to the power 3. Do you agree?
Yes, yes.
Yeah. So this is how you identify whether you're using this or that. For expressions like this, really, it's whatever works. You see as we go on and on, you find more expressions where, like the direct comparison, we see that even the direct comparison perhaps could have also, wait, this is the direct comparison. Also look at things like the limit comparison, where we'll have to even do more weird steps to get to the bottom of whatever we're trying to analyze. Okay, so this was the direct comparison. The next one that we'll now look at is going to be the limit comparison. Any questions?